Okay, good morning, everybody. So let's start. And today we are going to talk about the application of the deep kernel learning for automated experiment in microscopy, and specifically focus on the topics of the explainability and the human in the loop intervention. So first of all, let's have a recap of the topics that we explored in the previous several lectures. So first of all, in several lectures, we went through the primary topics of the Gaussian processing and Bayesian optimization. So we introduced the main concept of the Gaussian process. We discussed the kernel and kernel parameters, so what they are and why they're necessary. So the essentially kernel allows us to go from the points where we've done the measurements to all the other points. We discussed some subtleties of the Gaussian processes, so what are kernel priors, what are noise priors, and extension to the structured Gaussian processes when we introduce the mean function and the priors of the mean function. So basically the transition from the standard Gaussian processes to the structured one is already highly non-trivial. So this is not something that is described in the textbooks or even review papers. That's actually the area that emerges at the interface between the machine learning and specific domain sciences. So in some sense, if you're a machine learning expert and you want to work on the structured models, you actually need to pick up the knowledge from the domains. If you are a domain scientist, in order to follow this line of research, you actually need to have sufficient background in Gaussian processes in order to be able to write your own code with the adaptable mean functions and refine it based on the experiment. So we also talked a little bit about the Bayesian inferers and posteriors, sort of what is that? And putting it all together, we discussed the Bayesian optimization and the acquisition functions. So just as the general recall, so now we are going to go through this concepts one more time, but looking at slightly different aspects of the Gaussian processes than we did before. So from the very beginning, we discussed the situation when we have a one-dimensional parameter space. So this is just a scalar and one-dimensional function. So therefore, it is very easy to represent it as a graph. And at the same time, it represents certain amount of the experimental situations. For example, this can be a concentration in the binary mixture, or this can be a setting for one parameter on the aberration character. And this, of course, is a function represents the quality of the experiment. So notice one very important thing, that in most cases, we encounter the experimental scenario where x is actually not a scalar. For example, aberration character has much more than one controls. We can explore the phase diagrams which have more than one component. So then x will become a vector. Interestingly enough, in some problems, x can have a fairly complex nature. For example, imagine that you want to use the Bayesian optimization to explore the space of the defects existing inside the material. So in this case, the space is not continuous, but we still can run Bayesian optimization on top of it. We are not going to go there because this has fairly little to do with the microscopy. It's more molecular discovery problem. But Bayesian optimization can work on those spaces as well. Comparatively, y, or our target parameter, is actually usually either scalar or low dimensional. So if it is a scalar, then it represents something we want to optimize, for example, the resolution, or something we want to minimize, for example, beam damage. And for that, there are ways to treat the situation when y has several components, so we want to optimize them jointly. That's called the multi-objective optimization. And there are cases when we actually want to generate y to be multidimensional. So this is called the latent variable Gaussian models. Again, we are not going to consider it for the time being. So anyway, going back to the situation when x is strictly scalar and y is strictly scalar, Gaussian processing becomes the process of the following. We start with the several measurements. Based on these measurements, we try to reconstruct our function, and we try to reconstruct its uncertainty. So the classical Gaussian process is purely data-driven. We try to reconstruct the function based on the data only, and kind of hidden behind the schemes, behind the scenes, is also the priors on the kernel and noise. They're actually, in fact, exceptionally important. So Bayesian inference, comparatively, is when we know the functional form of our function and have some ideas of the parameters. Structured Gaussian process is when we put these things together, and basically our mean function, the Gaussian process, is essentially the probabilistic model. So we went through that. What do we do with that? Based on the Gaussian process, whether it is pure GP, SGP, or even Bayesian inference, we can actually define the policies for the exploration of our parameter space. So imagine that we want to learn this function that represented by the teal lines, the ground truth function. So if we do the Gaussian process reconstruction after 7 experiments, our reconstructed model curve, that our posterior mean, is very different. So it coincides with the function at the measurement points, but it is very different in most of the unmeasured points. So the purpose of the active learning is to find a place in order to do the next measurements to find this function as soon as possible. So the way it is done in the Gaussian processes is through in the purely exploratory mode, is by looking at the uncertainty. So you can instantly see that here, our uncertainty is fairly low. Here, our uncertainty is higher, and here, our uncertainty is highest. So the active learning experiment would take the next measurement point here, and if we take the next measurement point, we will instantly discover this minimum. That being said, very often Gaussian processes tries to do something more complicated than just discover the function. It tries to optimize the function. For example, if I tune the microscope character, I'm not really that interested in how it behaves away from optimal setting. What I really want to do is to find how the aberration character operates close to optimum so I can find those optimums. So how to tune my microscope sufficiently well. So in order to represent this optimization goal, Bayesian optimization creates what is called the acquisition function, which somehow combines the expectation of the function value and the uncertainty of the function value. There are multiple types of acquisition function: upper confidence bound, probability of improvement, expected improvement, and strictly speaking, you can always create more. So if you have an idea of what is that you're looking for in your experiment and how you want to balance uncertainty and prediction, you can come up with your own way to create and sample the acquisition function. And then the Bayesian optimization, so something that we've already seen, proceeds as following. Do 2 measurements, reconstruct the function and its uncertainty, create the acquisition function, do the next measurement at the maximum of the acquisition function, reconstruct the function and uncertainty again, calculate the acquisition function, find its maximum, and consider this project process until you run out of the experimental budget. So this is now well known and understood, but now we are getting into a very interesting area. So for example, you can say that, look, in real world situations, we always have a finite length of the experiment. So for example, if you run the experiment on the synchrotron, you have several shots and then your time is over and you can come back in half a year. If you run the experiment as the part of your research in the main lab, you actually have a much larger number of iterations. So should this consideration somehow be factored into the experimental design? And the answer is absolutely yes. So if you have a fairly short experimental campaign, so you have to run 3 experiments and this is it, you will go for very greedy acquisition function. So you will try to maximize gain. If your experimental campaign can be long, in this case, you will go for the more exploratory campaign. So you would like to see what are the options in the parameter space that you have. And only then you will become, you will start to favor the optimization goal. So if you think that this is very closely related to how we behave in real world, it is absolutely true. If you have only one shot at something, you will choose the maximum probability of success. If you have a considerable amount of time, then you will first explore the ground, and only with this new knowledge, you are going to make some significant decisions. So, but look at it from the other end. It means that if you create your, if you look at the Bayesian optimization loop, there are some parts of this loop that are the same, always the same. For example, training surrogate model, either using Gaussian process or structured Gaussian process or BE. But there are some things that actually depend on the external parameters. So the acquisition function we choose actually depends on our expectations for how long our experiments can be. This is actually very important. The second thing that you can ask a question is, does the acquisition function have to be always the same throughout the whole experimental campaign? And the answer is not necessarily. In fact, we can start with our experiment with the acquisition function that favors pure exploration. And over the progression of the experiment, we can make this acquisition function more and more greedy. In fact, we can even switch from Bayesian optimization and building the surrogate model. We can actually switch to, at some point, to the gradient descent methods, because if we have a convex optimization problem, meaning that we have one minimum, gradient descent actually works remarkably well. So what does it mean? It means that if we explore a function like this, we generally want to use something like Gaussian processes in order to discover all minima. However, once the minima are discovered, we can actually change our strategy. So once we know that one of those minima is deeper than others, we can explore them using the gradient descent. So in other words, we should not be limited by one specific algorithm and one specific parameter setting. We actually should be able to intervene at some point. And here comes the interesting point. Point is that in order to intervene, the process need to be run on the time scale where human can actually provide intervention. And that's actually what we are going to talk about today. Now, what about the self-optimization microscope? So for the time being, it was very general, and the sort of how does it apply for the real world scenario? Well, the problem is that we, of course, can use the Bayesian optimization for multiple parts of the microscope workflow. We can use Bayesian optimization for tuning the microscope and make it work better. It turns, however, that we really cannot use simple Bayesian optimization for exploration of the image plane. So I've shown you the example of the use of the simple GP as the part of the workflow on the scanning probe microscope. So something that we've done about 3 years ago. Turns out that it works. It is very expensive, and the results are really not worth it. So if we try to use the Gaussian processes to explore the image plane here, the results are really not that impressive. So why is it the case? This is exactly the reason why we are going through the detail of the Gaussian processes and the kernel function, because by now you're already familiar with the fact that kernel function represents the spatial correlations in the system. So the problem is that if our image have very sharp edges and a lot of small features, the kernel cannot represent them very well, which basically means that we need to have a very dense measurements. And in this cases, Gaussian process doesn't offer any particular advantage compared to the grid measurements. In fact, grid measurements are better because the scanning process in the instrument is also simpler. So then you have to ask the question, look, maybe this is, we should look at the Bayesian optimization in the same type of picture from slightly different angle. And in this particular case, the angle is that this axis no longer has to be a scalar. So we still want to optimize something. So our vertical axis is the scalar. So we have something that we want to improve. However, the horizontal axis can be something more complicated. And the typical problem that emerges in the context of the microscopy, either electron or scanning probe microscopy, is the discovery of the structure property relationships. So to summarize, classical GPU works in low dimensional spaces. The fact that kernel function defines correlation is limiting. We don't use any knowledge about the physics. We don't use the cheap information available during the experiment. Practically, if we use the deep kernel if we want to run the automated experiment in the SPM or electron microscope, we actually need to solve slightly different tasks. So rather than treating our image plane as a black box where we want to perform measurements, we need to run the automated experiment almost the same way as the human will do that. Meaning that when we choose the locations for measurements, we choose them based on the available structural information. So in the electron microscopy, it can be either CM data or HUDF. In the scanning probe microscopy, it can be one of the channels available to the scanning probe microscope. And here we come to the point of the deep kernel learning that Kevin has talked about in the previous lecture. So in the typical deep kernel learning scenario, we solve the problem as following. So imagine that we have access to the full structural data set. So we have our overview image. What we want to do is we want to find the locations for the spectroscopic measurements. It can be EEL spectrum, it can be force distance curve, it can be in AFM some form of hysteresis loop measurements. So we want to find the optimal locations for these measurements. Now, in machine learning, active learning, you always need to specify what problem you want to solve, because depending on the problem that you are trying to solve, your experimental path would be different. So one problem we can set in this context is to find the structure property relationships in the shortest number of steps. So structure property relationship means that we build the relationship between the local domain structure and the shape of the hysteresis loop. So if ultimately what we want to have is an oracle that takes the structure and can predict the hysteresis loop shape. So there are other tasks we can solve. For example, another task can be optimization. We want to find all the microstructures that correspond to the largest area under the hysteresis loop. Notice that these are very different tasks. So the discovery of the oracle, building the oracle that allows us to reconstruct the structure property relationship, is a very different problem than finding all microstructures that maximize the area under the hysteresis loop. However, practically both of these problems can be solved by the Bayesian optimization. One is the knowledge discovery problem, another is optimization problem. And the way to do that is through the deep kernel learning. So as Kevin illustrated, deep kernel learning is basically a combination of neural network and Gaussian process. What the neural network does, it takes the image patches and compresses it down to the low dimensional embedding vector. So it can be as small as 2-dimensional. And then the Gaussian process builds the relationship between the embedding and the target functionality. So you can reconstruct the full loop, or you can reconstruct just the area under the loop. It sort of doesn't matter. Kevin shown you the example of both of those. So the important thing here is that theoretically, we can do the same type of problem using the variational autoencoders. So we can take all our structural data, encode it to the latent space, and then explore this latent space to find the optimal functionality. The problem is that However, it works only if and only if there is a very strong correlation between the specific features and specific areas on the loop, because the latent space of the autoencoders are static, they don't change. And they're absolutely not bound to represent the functionality that we're interested in the optimal way. Comparatively, the latent space of the deep kernel learning are dynamic. So this latent space is retrained each time we give the network a new example. And in doing so, it finds the optimal embedding for our data. So this is the reason why in the examples that we worked with, the deep kernel learning works considerably better than the variational autoencoder. It's just the dynamic nature of the learning process. There is, of course, a price because VAE will work equally well or poorly, if you will, for any optimization task. Deep kernel learning will work well for the task on which it was trained and will work much worse for the tasks that it was not trained on. So that gives us to the point of kind of looking the whole workflow of the deep kernel learning based Bayesian optimization. So we start with the structural data. We measure a spectrum. It can be EELS, it can be Ronchigram, it can be anything depending on what type of experiment you run. You define the scalarizer. So ultimately, this is the functionality that you want to optimize for. You train the deep kernel, you do the measurements, of course. You train the deep kernel learning model. You define the policy to balance exploration and exploitation. You decide next position, and then you continue the process. So this is how we run the active learning experiment on SPMs or electron microscopes. And in principle, the same approach can be applied for any microscopy with a spectroscopy. So you can use it for SEM if you have non-indentation. You can use it for any electron microscopy if you want to detect the EDX or any other signal. So any technique whatsoever. The key parts are definition of the scalarizer and the policy. So you have seen, now notice several interesting things. So in the examples that Kevin have shown and the ones that I'm going to show in a few minutes, we define the physics that we are interested in at this stage, and we do not change it during the experiment. We define the policy to balance the exploration and exploitation at this stage, and we also don't change it during the experiment. So in other words, we configure our experiment with some parameters from the very beginning, and then this feedback circle kind of run automatically. So Kevin shown you the example of how it works in practice, so that it is something tangible rather than kind of dry concept. This is the example of the automated experiment in STEMILS, where our scalarizer is the ratio of peak at low energy, around 5 eV and 15 eV. So here we go. So this is the example when we did the measurements, defined our scalarizer as the ratio of the two peaks. And this is the example of the microscope that basically explores our image plane looking for those two peaks. So you've seen this example when we show that this approach works for the different flakes. But now look at this data from slightly different perspective. So we can see that the microscope have consistently taken the measurements in some special location. So here, it really like this edge, but not this edge, and not this edge, and not these edges. Here, the microscope preferred to do the measurement at this location and this location, but somehow decided that this edge is not interesting. So why does it matter? It matters because we defined our scalarizer in the most general way. We just said that this is the ratio of the two peaks, right? It's not very specific. It's actually fairly broad. We believed at that time, and we still believe, that this is fairly broad definition and fairly flexible definition. So why is it happening that here the points are concentrated and here the algorithm does not want to explore? So one way to look at it is to say that there is something special about the physics of these regions. But notice one very important thing, that if we specify that there is something special about these regions, we need to be able to explain what it is. There is a second way to look at it. So for the time being, our algorithm had the policies and scalarizers set in advance. And as a good scientist, we actually kind of should have some idea about how does the tool that we selected, how do they work? So what is special about them? And generally speaking, we cannot claim that there is something special about the physics of these regions unless we have 100% certainty of our machine learning model, which we don't. So for the first experiment, that's fine. I mean, the first experiment, the task is actually to make it work. After that, it's a little bit different. So again, we know that we can change the scalarizer just to make sure that things are roughly okay. So this is the example of the scalarizer when we look at the total peak efficiency. And then we need to start to look at areas other than electron microscopy. So we also implemented the deep kernel learning on the scanning probe microscope. So in this case, the situation is slightly easier because we understand the physics of some synthesis systems better. So you see an example of the deep kernel learning network actually talking to the microscope through the LabVIEW connection. And this is the example of the automated experiment where we start to explore the ferroelectric material, trying to understand in which areas the hysteresis loop area is larger. And you can see that here the color code is the measurement step. So you see that the instrument explored this location, then explored this location, then it discovered this location, and then it basically stays and explores this domain wall. If we change our scalarizer, so rather than measuring the hysteresis loop during the field application, we measure it in the off-field configuration, then the microscope explores these locations, and then it discovers that the properties are maximized along this line. So this works, and in this case, we can explain it. We can explain it based on the general knowledge of physics, but okay, there is a difference between explain and rationalize. So in this case, it's more like rationalization. We expect that the physics of these materials is such that the behaviors we're interested in would be maximized on this specific domain walls. So we didn't know it in the beginning, but after we got the experimental data, it sort of all makes sense. Again, this is not always true. So let me show you another example when we run slightly different experiment. So we measure our signal as the function of the magnitude of the AC voltage. So for linear material, this would be straight line. For real material, this would be a curved line. This curvature appears because of some domain dynamics, so how the domain walls and the material respond to the electric field. So the way we can run the automated experiment is we take the measurement at one location, we fit it by the cubic curve, and then we can run automated experiment when we try to find all the regions where we maximize A, so make it as non-linear as possible. We can run the experiments where we maximize B, or we can run the experiments where we maximize the ratio of A to B. Okay, so the moral for today is to make the presentations from home, because this is kind of horrible. Anyway, so in this particular case, we see that the exploration pathway is the following. So we explore several locations, but you can see that after a while, the algorithm decides that this region is particularly important. So this is another example. So this is a Hafnia, kind of very popular material these days. And you can see here that the algorithm have explored several locations, and then it consistently gets stuck into these two locations. And again, you may start asking a question. So does it mean that there is something special about this location that makes them particularly nonlinear? Or is there something about the algorithm when there is a trapping of our search in the specific locations? So remember, I've shown you in the example of the Bayesian optimization, I've shown that the Bayesian optimization methods can get trapped in the local minimum as all measurements. If your algorithm is greedy, you will get trapped. If your algorithm is very much not greedy, you're going to explore all the locations equally. So the problem is that in advance, you really don't know what is being too greedy or not too greedy. And then you can ask a next question. So can we somehow intervene and change our scalarizers or policies during the experiment? So let's assume that for whatever reason, you don't like this behavior. Can we somehow intervene once we are running the experiment? And that's exactly where the concept of the human in the loop comes into play. Does it happen in electron microscopy? Of course. So this is the example of the automated experiment in 4D STEM that Kevin has been running. So this is our acquisition function. This is our HUDF image. These are the locations where the measurements are taken. Obviously, once the measurements are taken, we take it away from the available scanning points. And you can see that in this case, the algorithm in the beginning have explored several locations. So far, we are good. And then it decided that it wants to get stuck in these two locations. So one location is the center of the hole, and one location is the corner of the image. So if you look at the previous example, exactly the same thing. We explored a little bit throughout the material, and then we zoomed in on these two locations. So same thing here. We explored the material. We have been updating the acquisition functions, and we always do the measurement at the maximum of the acquisition function. And for whatever reason, our criterion for the acquisition function really highlights these locations. You can speculate that if we continue our experiment for some time, we'll start to do measurements here and here. But notice one very important thing, that the acquisition functions in the imaging experiments are usually very shallow, meaning there is no big difference between this location and this location, which basically means that if it is not shallow, that means it would be very sensitive to the small details of policy that we choose. So what can we do about it? So let's look at the situation one more time and say that in conventional microscopy, and look at the difference between the conventional microscopy and machine learning driven microscopy. So if we run a conventional microscopy experiment, human runs everything directly. You define the scan, you position the probe, you define the measurement parameter, you hit the button and you do the measurement. When we run the microscopy with the automated experiment, we define the policies before the experiment. So in case of the Bayesian optimization, the policy is the selection of the scalarizer and the acquisition function. Sometimes it works, but it not always works. Which basically brings us to the same question that I was kind of going around through the whole lecture, minus the interruptions for the internet connectivity. And the question becomes, how can we explain the progression of automated experiment after the experiment? So how we make it explainable and how we can control it during the experiment. Notice that many of you have heard the keywords about explainability, human in the loop, and whatever, reinforcement, human in the loop reinforcement learning. So roughly we are addressing the same problems, but we are addressing them from the point of view of the experimental physics. And unfortunately, we cannot use the large language models to help us solve the problem here. We need to come up with our own solutions. So let's again take one more time, take a step back and just look at what is our toolbox for the automated experimentation in microscopy. So we have seen the examples of the direct workflow. So when we talk about the use of the deep convolutional networks in real time, so this is how it works. We acquire raw data, we label. So this is a lot of human work. We train a deep convolutional network. There are some details here, as we discussed, that if we just train the network, it will work for exactly the same microscope settings, but not others. So we need to find ways to generalize. Typically, it's done through the ensembling. But that if we've done it, trained network can analyze the data which is on the fly. So the microscope produces the data, and the network analyzes it and finds the objects that we're interested in. And then we can perform the experiments based on this predefined workflow. So this is the direct experiment. In this case, the policies are fixed. So the policy is fixed twice. First of all, we train our network based on the data acquired before the experiment. So we don't retrain it. So this is defined our prior knowledge. And then our policies, meaning our actions, are also defined in advance. So our policies can be find all the defects and do the measurements on this type of defects. So the Bayesian optimization is an example of the myopic discovery. So in this case, we acquire some seed data, evaluate it, kind of decide whether we have to proceed with the experiment or not, train Bayesian optimization model, then plug the results in the predefined acquisition function, acquire next data set, and kind of continue doing this type of stuff. In this case, the policies are adjustable, but we plan only one step ahead. So there can be more complex multi-stage discovery workflows, but we'll get to this point by the end of the presentation. So now the question becomes, let's look again in the main workflow of the Bayesian optimization and try to think how the human can affect this process. So how can we intervene during the experimental parameters, during the experimental process? And the answer is that, first of all, while we're running this experiment, we can change our opinion about what physics are we interested in. So I've already shown you example of the two experiments for scanning probe and for electron microscopy when we changed the scalarizer. And of course, at that time, it was done kind of between the experiments, but there is no reason why the scalarizer cannot be changed during the experiment. Secondly, again, I mentioned during the while discussing these examples, that we can change the policy. So we have always ways to tune the knobs that balance the exploration and exploitation. So typically we fix the policy, but it doesn't have to be. So human can actually change this while we're running the experiment. And then you can ask the questions, okay, so we have these knobs. You have seen the codes that show how these parameters can be changed. But the question becomes kind of how do we know how to change them? And this is the case where we need to come up with the ways to monitor the progression of the automated experiment, like we are doing here. So we can monitor the progression of the automated experiment, and we need to make the decisions based on how this experiment actually proceeds. Okay, so what we need to do is the monitoring signals. The problem is, of course, that if we try to do something like this on the real world microscope, this is not the most kind of conducive environment for the development. Usually when you deploy the code on the microscope, the code should already work, and the code should already work, and it should be already kind of more or less be optimized. So the best way to develop this type of workflow, and also an important thing is that microscope never remains stationary. So your beam tuning start to drift, your sample accumulates damage. If you do the scanning probe microscopy, then your probe can be damaged. So basically, the way to develop this type of workflows is actually to do it in the dummy experiment when we generate large volumes of the prior data, and then we treat this pre-acquired data as if we are running the experiment. So the more data you have, the easier it is. Obviously, so in this dummy experiment, we generate patch spectra pairs from pre-acquired data, and we can define the scalarizers and do whatever we want. So the good thing about the dummy experiments is that we can run the same experiment many times and see what the difference is going to be. For example, we can change the scalarizer, we can change the acquisition. On real microscope, we will not be able to do it because if we run the automated experiment several times, by the end of it, we simply will not have a sample. So in real experiment, comparatively, we have all the patches from the beginning, spectra acquired sequentially, but we get to do it only once. So how it's going to work? So I'm going to show it in the notebook, but let's look at the example. So imagine that we have the EELS experiment, and we have access to the full three-dimensional EELS dataset. So from three-dimensional dataset, it means that we can average it, and then we create quote-unquote dark field image. And each pixel of this image is actually the EELS spectrum. So this is actually a projection of the three-dimensional data set. This is a single point. So it's convenient because we don't need to deal with the alignment problem. We don't need to deal with the drift. We just kind of operate on ideal microscope. We cannot do new measurements, but the measurements that we have are already good. So the first thing we can do is we can define scalarizer or scalarizers. So for example, for EELS spectrum, I can choose a scalarizer as this intensity integrated over this interval. And this is how it looks like. This is our image of our scalarizer. So this is a different scalarizer. So let's assume that I want to integrate intensities here. And this is how this one looks like. So again, given that we are operating with the pre-acquired data set, this is just relatively low resolution images, but again, it is what it is. So once we have the full data set, we can actually do an interesting, if not particularly obvious thing. We can train our deep kernel learning model given the full data set. So you can say that this is not very practical because after all, we are using the deep kernel learning in order to run that automated experiment. So what do we get if we train it using the full data set? Several things. First of all, we can see how well the model can work in principle. So this is the ground truth. So the deep kernel learning model builds the relationship between structure and scalarizer. So structure is an input, scalarizer is an output. So this is our ground truth. This is the prediction. So interestingly, the prediction and the ground truth look almost the same. So the prediction is a little bit smoother. That's actually good. It's also not very useful because that basically tells you that we kind of predict based on the training data, like what's the purpose. That being said, notice that denoising is also prediction based on the training data. So it's useful, at least from this perspective. However, remember that the deep kernel learning also gives us uncertainty as any Gaussian process. So why is that useful? It is useful because the uncertainty tells us already where the model is kind of self-consistent and when it is not. And you can see that in most parts of the image, the uncertainty is actually fairly low. It is fairly low because the model can predict itself. But interestingly, the model says that, you know what, I'm not particularly excited about the predictions in these locations, and I'm not sure what happens here. Why does it matter? It matters because the model itself intrinsically raises a little bit of the red flag about where the outliers. So the model works well here, here, and here, but these locations are somehow different. Maybe you should pay attention to that. And then, of course, we also get the embedding vectors. So embedding vectors, what they mean in DKL is the kind of open question. For the time being, let's assume that we can just visualize them, and that gives us some parsimonious representation of the system structure. So the important thing about this embedding vectors is that we can interpret them similarly how we did for the latent spaces of the variational autoencoders. We can say that they disentangle the relevant behaviors of the data. So this being said, this is great. We trained the full model we have trained the full the full model on the data. The question becomes, why is it useful? And it becomes useful because we essentially created an oracle that we can compare to the real-time experiment. So what I mean by that is that when we start the experiment in the beginning, we can monitor the progression of the learning by the deep kernel model. So in the form of the uncertainty. The model, which has been pre-trained on the whole data set, allows us to compare the learning curve to the maximum amount of the information we can learn about the system by the end of the experiment. It's if you sometimes ask yourself a question, if I go back in time by several years, what would I have done differently? So in real world, we never have this option. But if we run the dummy experiments, we actually can. So what we can do is we can create the models. The live model is the model as it is on the microscope. This model shows us the learning process. But we also can create two additional models. One is the final model, and the third is the complete model. So final model is the model that knows as much as we would have known in the end of the experiment. So in the beginning, we learn. In the end, we fix our knowledge and we create the final model. And then we can compare the learning and predictions between the live model and the final model. And in case of the dummy data sets, we also can create the complete model, which is trained on the full volume of data. And again, we can compare the prediction and uncertainty. Now, there are several now we are going to the question of monitoring. So how are we going to monitor the live automated experiment? And the answer is that we need to monitor the things that the deep kernel learning model gives us. It gives us the uncertainty for each for each patch. And if we have the uncertainty for each patch, we can do two things with it. We can calculate the average, and we can calculate the uncertainty. And now the interesting things happen. So let's assume that we run the deep kernel learning-based workflow several times. One time, we run it using the acquisition function, which is maximum uncertainty. So in this case, it's a pure learning process. So what we are going to do is we are going to monitor the prediction uncertainty, and we are going to average it for all the image patches, and we are going to calculate the average and dispersion. So look what happens. So if we start the experiment, our predictive uncertainties start to decay relatively fast. So it's a relatively steep curve. And the dispersion of the predictive uncertainty also is relatively small. So in other words, we learn to predict the structure property relationships reasonably fast. Notice another thing is that our final model and our complete model have a fairly narrow distribution of the predictive uncertainties, meaning that we expect to predict for all patches reasonably well. Now, let's assume that we change our acquisition function. So we use either UCB, the upper confidence bound, or the expected improvement. Notice that our learning curves are completely different. So in this case, when we use these functions, they are greedy. They don't try to learn in the sort of academic fashion. They try to optimize our scalarizer. And you can instantly see what is the price for the optimization of the scalarizer. So our learning process is much more uneven. Our predictive uncertainty is much more broad. And the reason is because from the early on, we focus our attention on the specific patches and we ignore other patches. So for the specific patches that we're interested in, we discover them over and over again. The ones that we ignore because we don't expect them to be useful, they result in the uncertainty to be large. So if you compare the uncertainties for the final model, it remains remarkably broad. The complete model is obviously the same in all cases because it's trained on the full amount of data. We don't select. And for more greedy function like EI, the situation is even worse. So in this case, our uncertainty decays fairly slowly, and the distribution becomes very, very broad. So this is actually takes kind of a little bit of time to learn how to interpret these curves. But once you did, this is something that is a black curve is available during the experiment, meaning we can use it at the real-time monitoring of the learning process during the deep kernel learning process. So what else can we monitor? We can monitor the trajectory. So this is the example of the same data set where I have simulated the deep kernel learning process using the expected improvement, maximum uncertainty, and upper confidence bound. You can see that the exploration trajectories are very different. So given the scalarizer that I've chosen, both my EI and UCB have explored the outer envelope of this cluster of particles. They kind of probe the situation inside a little bit, but not much. And they just spend quite a lot of time exploring this standalone particle. Notice that this standalone particle had been explored in the earlier stage of the process. And after that, it does not satisfy our conditions of the scalarizer. So we kind of decided to stay inside. Comparatively, if we try to use the maximum uncertainty as the policy, we actually explore the edges and we also explore the central part. Interestingly, we almost don't explore this particle here, and we, for whatever reason, don't explore this part of the object. So it's a good state forward. So when we run the experiment, this trajectory is also available in real time. That's something that we can observe, and this is something that we can make decisions of. For example, if my algorithm keeps exploring this area, I can switch the tune the acquisition function so it starts to explore this part more because I think that this is more interesting. Now, the next question becomes, can we learn what is special about this location? So why is the algorithm exploring specific these locations but not others? And the answer is that we need to have some way to understand what these locations are. And that's exactly the case where we can use the operational autoencoders. So VIEs will basically take, we can take our visited locations and run the VIE analysis. So in this case, we already talked about what it means. So it's our latent space. And of course, we get the distribution, all the points that we visited become some form of distributions in the latent space of the autoencoder. So obviously, each pathway has its own latent space. So we cannot compare this point and this point. We can only explore the trajectory in the latent or feature space of the same system. However, we can also introduce the global latent space. And the global latent space is all the features that are in the system. We can, so this is the example of our patches here. We can create the latent space. So now these features are ordered and we disentangle their representation. And then all the data, so the global image and all global image patches, become a latent distribution. And we can also plot the corresponding latent images. So that's something that we have done in the VA lecture. And as I mentioned, the VA is the foundation for more complex analysis. And this is exactly the example of how it works. Now, the interesting thing here is that we, of course, can choose the representation that we want. We can use the rotation invariant VAEs, we can use joint VAEs. It all depends on what specific problem you want to accomplish and what specific factors of variability are you interested in. And then the trajectory for each automated experiment essentially becomes a trajectory in the latent space of the full feature space. So this is our feature space. This is the green contours is the kernel density estimate. It basically shows us what is the density at which different elements are present in the feature space. So we use it instead of the latent distribution. And then for each acquisition function, we can basically visualize the points that has been visited during the automated experiment. And you can see that there is a pretty consistent difference between the, let's say, maximum uncertainty and the UCB and EIA sampling. So the maximum uncertainty, for example, explores these features quite a lot. And these features correspond to these double edges. So, for example, these ones. So the double edges are exactly the features that define this central element here. They're just represented as the latent space of the variational autoencoder. Comparatively, the UCB and MU and EI spend quite a lot of time in this location of the latent space, where you just have the small classical edges, and these are exactly these regions. So these methods explore the edge of our patch more than anything else. So putting it all together, how do we put the human in the loop? So first of all, we define the monitoring signals. For the time being, our monitoring signal is the learning curve. So how does the DKL model acquire knowledge? Where we can introduce the oracles. So the oracles are the full model and complete model. In real experiment, you don't have access to them, but the learning curve by itself is already a very good indicator of how the DKL works. We define the real space trajectories, so that's something that we observe during the experiment. And we can define the evolution of the system or exploration path in the feature space. That one requires a little bit of getting used to, because it requires the variational autoencoder based representation. But again, we have access to it before the experiment, therefore we can use it to observe the experimental progression. So this is our observables. And then these are our points of intervention. So when we run the automated experiment, we can define the initial exploration targets, so the seeds, but we also can define the new one during the experiment. So as simple as that, you can choose your experimental path and you can click on some location of the screen, and then the instrument will do the next measurement at the location that you suggested rather than someone else. Interestingly enough, we can also do it in a more systematic manner. For example, if you see something on the screen, you can actually indicate that these are either initial exploration targets, or these are exploration targets that you injected into the automated experiment process. So for small images like I've shown, which are barely 100 by 100, it's not immediately obvious why it is useful. Once you start working with the images which are 10,000 by 10,000 pixels, that becomes obvious very, very rapidly. So the second thing is that we can intervene on the scalarizer. So what we can do is we can either switch between the different scalarizers, or if the scalarizer have certain controls, for example, the width of the spectral peak over which we integrate, we can actually tune those as well. And then we get to intervene on the policies to balance exploration and exploitation. So we can make it more greedy or less greedy. So why is it interesting? So it is interesting because overall, we are looking at the future of microscopy that is going to be very different compared to what is the present. So the present is human sitting in front of the microscope. Human issues the basic commands. The microscope produces images and spectra. Human kind of looks at the images and looks at the spectra, makes some decisions and issues the basic commands. So to the best of my knowledge, virtually all microscopes worldwide work like this. So once we have the machine learning agent, the situation is totally different. So of course, human can also can still introduce the basic commands. That's possible. But generally, we expect the machine learning agent to issue the basic commands and analyze the image and spectral data. And what the human does is not primarily kind of introduce the commands. What the human does here, the human monitors the performance of the machine learning agent and changes the policies that machine learning agent follows. For example, we can increase the curiosity in the ML behavior, or we can say we can change the goal at which we want the exploration algorithm to pursue. So notice that it is very unusual because from now in this setting, it's not us who run the microscope, it's us who kind of tweak the agent that runs the microscopes. Now, a very interesting and to some extent philosophical questions of whether we can envision more complex workflows. So obviously Bayesian optimization or myopic workflows is a very narrow class of the specific workflows. And by virtue of it being a very narrow class, it makes sense to look at the broader workflow. So imagine that rather than trying to learn the structure-property relationship, I'm trying to do something much more much more general. So I try to optimize imaging parameters. I try to scan image. I try to optimize spectroscopy parameters. And then I start to explore statistically relevant regions. I want to explore outliers, so meaning curiosity-driven research. And then I start to explore regions given the specific hypothesis. If I know that I'm interested in the ferroelectric domain walls, I'm looking at these regions. If I'm interested in ferroelastic domain wall, I'm looking at these regions. And then a very interesting philosophical question is, what type of machine learning do we need to solve this type of problems? So one way to look at it is to say that this is a multi-stage optimization. This is probably a classical reinforcement learning problem. That is, strictly speaking, correct, but I am not sure that the reinforcement learning algorithms would be particularly useful for many of these problems. And the reason why I'm not sure about it is because reinforcement learning in its basic form requires very large volumes of data. So in other words, we need to run the experiment very many times. And of course, we don't have this opportunity in the experimental studies. The alternative is to use the reinforcement learning with the strong models, meaning the kind of the type of RL scenario when we train the model, we have the trained model, and then we update the model based on the experiment, but the RL decisions are informed by the model much more than by the experiment. That is entirely possible, but for the time being, I have not seen examples of non-trivial RL use in microscopy, sort of beyond the single-stage decisions. What I think is that realistically, at least for the next several years, it will be the human in the loop interventions that will define the experiment, because all of this, we can optimize this workflow either from the end target, and then we have to use the RL and go through it many, many times, kind of classical TD lambda learning, Or we can monitor the progression of the experiment and basically choose the use the human in the loop approach in order to switch between the different optimization targets. So that seems to be more close to the way that humans work now. We'll see whether it is the case or not. But one thing for sure is that transition from the human running the microscope to the ML agent running the microscope is not exactly like moving from driving Toyota to driving Lamborghini. It's much more like transition from riding a horse to driving a car. So the tools that we use are totally different. So this being said, in this particular case, there are several definitions that we have. So they're also available in the preprint that I've sent around. And let's spend several minutes looking at the how this forensic experiments can be realized using the GPAX approach. So I have put the notebook on the lecture website, so you will have access to it. So this notebook defines the explainable ML and human-in-the-loop intervention for automated experiment for the STEMILs. So as you can imagine, that has been a fairly large project, kind of initially started from the kind of GPAX library developed by Maxim. The initial workflow was built by Yongtao, adapted for use by Kevin. Then, of course, there is a kind of long story of the sample acquisition. So this is exactly the same picture with the ML agent controlling the microscope. So let's look at what's inside of this notebook. And as in the examples before, we will not be able to go through the beginning to the end. First of all, this is already fairly time consuming. So this notebook takes about a day to run on the normal Pro Plus Colab. And secondly, let's just go through the main elements of the code. So as before, we have the imports, we have the definition of some helper functions. So in this particular case, these are acquisition functions. So the interesting things start here. So this is the download of the STEM-ILS dataset. So as before, we can take this dataset and explore what's inside. Basically, this is just a collection of the ILS dataset acquired on several locations in the plasmonic nanocubes. So you have the structure formed by 7 particles, you can have an edge, you can have this blob structure, you can have a long particle with the regions of the double particles and different ordering. You can have this type of region, so when you have an edge and you have a standalone particle. So basically pick the one that you like. So in this notebook, for this example, I have chosen the example number 9, so this one. And basically the first thing that we need to do is to define the window sizes and define the spectral averages. So we really don't need to have all the channels. That becomes kind of complicated. So then basically up to this moment, this is the part that defines our data set. The obvious way you can use this notebook for your own data would be to look at the data structure here and substitute the data object that we use by the data object that you want. So that's a way how you can adapt it from STEMILS to CITS or AFM or EDX or any other measurement method. So the interesting things start here. So first of all, we need to define our window size. So in the dummy data sets, we do that because we operate with the pre-acquired data. On the real microscope, you will kind of have more flexibility. And then we define our coordinate grid. So this is absolutely standard operation. So we got the function in Atom AI that allows to create it. And then we basically create the our data set as the collection of patches, spectra, and coordinates. Again, since we have to run this, given that we have to run this many times, there is a special function in Atom AI that basically allows to do that. So, and then we look, and this is what our dummy data set is. So we have 1400 objects. So the spectra are about 1,000 long. Coordinates that determine where the spectra came from is XY, and the patches are 8 by 8. So this is how our data should look like. If you run these measurements on the live instruments, then you obviously have access to these two objects, so to patches and the sampling points. You don't have access to those ones. They become available sequentially as you do the measurements. So then, of course, we can explore how the data look like. So for example, this is the window centered at the chosen location. This is it in the global image. This is how this window look like if we zoom in on it. And this is the spectrum acquired from the center of this window. So we cast our problem as the patches and spectra. So the next step for us is to create scalarizers. So we don't want to reconstruct the whole spectrum. We want to optimize for specific behavior. So here Kevin have come up with the list of the scalarizers. So one is the coupled dipole mode, which is the basically spectral average between these two locations. So this is how it looks like. This is another scalarizer, which is the edge mode. So this is how this one looks like. So again, this is a ground truth. In the real experiment, you will not have access to the scalarizers. In the dummy experiment, we can kind of choose them whatever we want, and we can redefine them over and over. So the third scalarizer is the bulk mode, which is the spectral average. So we have three. So, and then we go through the running of the deep kernel learning on the full data on the complete model. So this is a creation of our oracle if we run an automated experiment. Of course, we don't have access to the oracle during the experiment, only afterwards. Or this is generally looking at the data set and trying to denoise it, find the embeddings, and so on and so forth. So let's run the DKL with the two latent embeddings. So this is our ground truth image. This is the mean prediction. So it looks like the smooth version of this one. This is the variance. So variance is uncertainty. Notice that there is one region where the uncertainty is high. So there may be something interesting going on there. Again, we can visualize the latent variables. So once we visualize the latent variables, whether they change us, tell us something or not, that's an open question. In this particular case, it looks like they are almost the same. So it's the same problem as the dimensionality collapse, representation collapse in the variational autoencoder, which basically means that we have only one factor of variability. So, and then we can see how this latent images look like, meaning superimpose the latent embedding on the original image. So far, so good. So we already can learn something like this about the physics of the material, the extent of the plasmons, and quite a lot of other stuff. So we can also run the same thing with the three embeddings just to see how things look like. So we obviously compare the predictive mean, did it improve or not? We look at the uncertainty, notice that now the model is more attentive to details, and now it's no longer sure about what happens here. Again, we can visualize the latent embeddings, latent space. So there are three components in this case. And now we can switch to the active experiment. So once we run it in the active experiment, we need to choose how we are going to run it. So for the time being, it is realized that we can choose one of the three possible functions. We define the parameters of this function. So for example, we define xi, which is the exploitation for the expected improvement. We define the number of exploration cycles, because we kind of have to. And we need to introduce some random state key for the GPAC. So obviously we use the one which is 42 because, as we know, the 42 is the answer for everything. So then, depending on how you use this notebook, you can either choose to explore all three acquisition functions or choose the one that you want. So to make it easier, we want to store the data. And here we start to train our model. So that will take quite a while. So we can also train the complete model, kind of available in the end of the experiment. And then we will download all the results because, as I said, the training part, even on this reduced version of the notebook that I made more as a tutorial, can take quite a while. However, we can upload the data. Notice that Google constantly changes the way they tweaks the way the notebooks are organized. So there were sometimes problems associated with the local state. So that was the solution. Now it doesn't seem to be necessary, but if things don't work, try to kind of uncomment it and run it again. And then we go to the visualization. So the first thing that we look at is the learning curves analysis. So this is the example of the learning curve for this particular data set. So this is how, again, it is important to pay attention both to the average decayal uncertainty and the dispersion of the uncertainty over the all image patches. So the average one tells you how well the model works on average. The dispersion means is how large is the variability from patch to patch. So if you use the purely exploration strategy, then they both kind of evolve smoothly, and your final model is gives you a fairly low uncertainty. If you have the models which are relatively greedy, then you can see that the learning characteristics is very different. So in this case, they don't try to minimize uncertainty, they try to optimize something. And interestingly enough, the uncertainty can even go up. So for example, for the very greedy function. And in the end, your model actually gives very different level of certainty for different patches. It sort of focuses attention on some of them and ignores the others. Sorry, what did I do? So another thing that we can look at is the behavior for each kind of the acquisition function behavior. So in this case, you can see that in one case it decreases, another it kind of fluctuates around. And we also can calculate the predictive value of the scalarizer for the next measurement. So you can see that in this case, for the exploration function, it kind of goes up and down because it really cares about the minimizing the uncertainty, not the scalarizer value. The ones where you try to optimize for a scalarizer will actually try to give you the kind of lower value of the scalarizer. And you can do the same things on kind of averaging out. So this is the next point prediction for EI. So you try to optimize. This is mu. It kind of tries to go up and down because, again, it doesn't care about the value of the scalarizer in the long run. So there are other things that we can do. So the classical thing in the Bayesian optimization is so-called the regret analysis, meaning how the selection of the next point, how the return from the next point that I've done a measurement would have been different have I had the access to the full model. So in other words, during the active experiment, we make decisions based on the partial knowledge, and therefore these decisions can be suboptimal. So the regret analysis tries to understand what would have happened if the knowledge in the end of the experiment were available in the beginning. So this is roughly what the regret is. Generally, the smaller is the regret, the better. So if your approach is giving you a large regret, that means that it is not optimal. If it is small regret, then it is optimal. Notice that we calculate the regret for a specific scalarizer. So if we use the EI or UCB, then the regret is relatively smaller. If we use the maximum uncertainty, the regret is initially very high, but then we learn and the regret becomes smaller than it was for the MUI and UCB. So what this tells us is that the greedy strategies are better in the beginning and then tend to be not so good in the end of the experiment. So then this part of the notebook incorporates the real space trajectory analysis. So this is just taking the points that we have visited and representing them in real space. And this gives us the feature discovery. So for each trajectory, we can define the experimental trace, meaning the sequence of patches that is visited. For each trace, we can visualize the trajectory in the latent space of the autoencoder and the sort of latent representation of the autoencoder. And we can do the same thing for the global space. So these ones are available only in the end of the experiment, and they are specific to the trajectory. The global one is available in the beginning of the experiment. So this is where we're getting to the global one. So the global one is available from the beginning of the experiment, and we can create the latent representation. We can create the latent images as before, and we can basically create the trajectory of the experiment and the latent space of the global system. And this is again something that we can visualize during the active experiment. Okay, so this notebook is, and again, for convenience, I provided the summary and the list of definitions, because once you work in the interface between the automated experiment and machine learning, there are a lot of new objects that needs to be introduced even to describe what is that we are doing. So I provide the list of those definitions. So let's stop here, and I apologize for the interactions with the internet. So that was probably the record for the school. And as I said, normally I expected to have a more stable internet connection, but again, it is what it is. So let me know if you have any questions. Okay, if not, then my general advice would be to play with the notebook and go through all these notions. So again, these concepts are not particularly simple, so it may take quite a while to go through them and internalize them and apply for your own problems. It shouldn't be that difficult with a notebook, but again, it's not simple. And thank you for your attention.